So in this one, we're going to look at the first of our types of circuits that deal with inductors, and this type is what's called an RL circuit. And it's called an RL circuit because it contains both a resistor and an inductor that are in series with one another. So here I have a circuit where there's a battery with voltage V connected to a resistor, resistance R, and an inductor with an inductance L. And we're going to look at what happens the moment I flip the switch to connect the resistor and inductor to the battery. Now, in this particular circuit with the resistor and the inductor, there's nothing that stores charge, so there should be zero charge and zero current the moment before that switch is flipped. But let's kind of look at what would happen. If we use Kirchhoff's rules, we get V minus IR minus L di over dt. Remember that the voltage or potential drop across an inductor is equal to L times the change in current. So the one thing I would say at this point is take a step back and look at your circuits, or look at your notes when we talked about the RC circuit, and notice the similarity in this equation between the charging of a capacitor of an RC circuit. The only difference is we had Q and dQ dt, here we have I and di dt. So what would actually happen if we actually work this solution out is we would get that the current as a function of time looks like this equation here. V over R times 1 minus e to the negative R over L times t power. So what this would mean is that initially the current should be, well, 0 initially, and the change in current would be maximum. If we plugged in 0 in here, you get 1 minus 1, 0, 0. The voltage across the resistor should be 0 since V equals IR, so the voltage across the inductor should be equal to the voltage of the battery. What this means is that we can calculate di over dt initially by doing voltage in the battery divided by the inductance of the inductor. It's worth pointing out that this is the maximum di dt in this circuit. So what happens as the current begins to change, or we can almost think of it as the current begins to build up, is that current increases, voltage in the resistor increases. That means voltage in the inductor decreases, so change in current decreases. So we'll actually end up with some steady state if we were to plug an infinite value in here. What you'd end up with is that di dt is equal to 0. The current would be just V over R, and then the voltage across the resistor would be V. So really what the inductor in this circuit is doing is spreading out the change in current. If the inductor wasn't here, the change in current would be very high for an instant in time, and then you'd end up with V over R as the current. Instead of being a instantaneous very high change in current, adding that inductor slows that change in current down. And so you go over a much longer period of time increasing current. Now, like the RC circuit, we can define a time current constant for this circuit, and that time constant would be L over R. Remember that this value over here is really 1 over the time constant inside there. So if we look at the charging, or the flip the switch, what happens to the inductor as things happen, here's the current, and we end up with our steady state, which would be V over R up here. What happened if we flip the switch back over is that current would start to decrease. There's no longer that driving force, so we can actually prove that that's true. L over di dt plus IR. Notice again the similarity with the RC circuit. And so what you end up with is an equation that looks like that for current. The current decreases. Basically what happens since there's a potential drop in here, the potential starts to decrease, the current starts to decrease. The inductor induces a magnetic field to slow that decrease in current down. And so instead of being, normally if this is just a resistor that you did this to, the current would go to 0 instantaneously. Instead, the initial current ends up with like this, and it slowly goes to 0 based upon how large that inductor is. So really, if we go back to this graph, here's what the current would look like in the inductor if we flip the switch S as time progresses. So let's do a quick problem. Let's say we have a circuit to the right, and it has a battery with an EMF of 18 volts, and it has 3 identical resistors, all are 9 ohms, and 2 identical 2 millihenry millihenry inductors. And it wants to know what is the current through the battery at the instant the moment is the flip is or the switch is closed, and then what is the current through the battery after the switch has been closed a long time. Now, at the instant the switch is closed, remember that what the inductor really does is it opposes changes in current. So the two inductors act to prevent change in currents, and so initially no current goes through the inductors right after the switch is closed. And so all the current is going to flow just through the middle resistor. So if we actually work this out, here is what the equation looks like. I equals 18 volts over 9 ohms. So really what this circuit looks like is just one 9 ohm resistor in series with the 18 volt battery. Now after the switch has been closed a long time, well, the change in current goes to 0, and so the inductors no longer have any impact on current flow. So what this would look like at this point, if it's been closed a long time, is a circuit with 3 parallel resistors. So we can calculate the equivalent resistance of 3 parallel resistors. Really, 1 over 9 plus 1 over 9 plus 1 over 9 equals 1 over RQ. You get 3 over 9 equals 1 over RQ. RQ equals 9 over 3, so 3 ohms. And so the total current through the battery is 6 amps after a long time has progressed. So we can look at RL circuits, and a lot of times when I've seen them do an RL circuit, they look at the moment the circuit or the current or the switch is closed. So the moment you start to try to push current through the circuit, what's happened after a long period of time, or make you present a graph like one of these, what happens to current as time progresses. So in the next lesson, we'll look at what happens if we put an inductor and a capacitor in the same circuit with one another.